Hi, my name is Grace Murray, and I looked at the LED and semiconductor lab for my final experiment. For some background, what is an LED? An LED stands for light emitting diode. It's made of semiconductor materials and utilizes the movement of electrons and the overlap of valence and conduction bands to emit light. LEDs are commonly used because they last longer than incandescent light bulbs. They normally have about a 100,000 hour lifespan. They're brighter, and they only use about 10% of the electricity that an incandescent bulb would use. So LEDs work through the movement of electrons from the valence band to the conduction bands of closely packed covalently bonded atomic systems. As you can see in this figure right here, there is a band gap present between the valence band and the conduction band. And within both the valence band and the conduction band, there are energy levels signified by the black lines within the bands. When an electron is promoted from the valence band to the conduction band, it leaves a hole in the valence band and ends with an increased electron or carrier concentration in the conduction band. The gap here is called the band gap and is signified by EGI. The location of the highest concentration of electrons within the valence and conduction band determines the band gap width. As you can see on this graph on the bottom right, there is a point on this energy axis where there is zero carrier concentration, yet there is an energy difference. This is at the very top of the valence band and the very bottom of the conduction band. However, most of the carrier concentration actually occurs somewhere within the valence band and the conduction band. So, many elements in the fourth group on the periodic table are semiconductors, though conduction may only occur at extremely high temperatures. In order to increase the conduction, semiconductors may need to be doped with group 3 and group 5 elements. There are two types of semiconductors that occur after doping. The N-type, as shown here on the right, where there's a dopant band right underneath the conduction band, and electrons are promoted from the dopant band into the conduction band. There's also a P-type semiconductor where the dopant band is right above the valence band, and any promotion or any decay would result from the dopant band to the valence band. Promotion of electrons goes from the valence band to the dopant band. Both the P-type and the N-type alone, if they undergo any kind of electronic decay, would not result in visible light, as the gap between the dopant band and the valence band is not large enough to have wavelength emitted within the visible light spectra. So, in order to combat that, P-type and N-type semiconductors are combined together, where the decay from the conduction band to the valence band results in a larger wavelength that is visible in the visible light spectrum. This decay that results in visible light is only able to happen if the current is flowing from the N-type to the P-type, as will be seen on the next slide. So, if the current is flowing in a forward bias from the N-type to the P-type, the concentration of electrons in the N-type semiconductor can drop into the holes that are present in the valence band of the P-type. If the current were to flow from the P-type to the N-type, there is no large enough concentration in the conduction band that would create any sort of wavelength emission in the drop or in the decay. So, the combination of N-type and P-type semiconductors are known as homo or heterojunction diodes. The homojunction diode is just the combination of the N-type and P-type semiconductors. This happens when the intrinsic material, which is the material within the N-type and P-type band without the dopant, is the same for both the P-type and the N-type. So, additionally, the wavelength emission is determined and can be altered by adding a concentration of a dopant that would change the band gap between the valence and conduction band. More commonly used than the homojunction diodes are heterojunction diodes, and these are formed with P-type, N-type, and an active semiconductor. This active semiconductor found in the middle of the N-type and P-type is made with a different intrinsic material, and this has a significantly smaller band gap. This results in a much brighter or higher light outputs as well as more accurate light outputs and is often used within consumer LEDs today. So for this experiment, there were 5 total LEDs. There are 3 aluminum gallium LEDs, red, orange, and yellow, and then 2 indium gallium diodes, which are the green and blue, and 1 semiconductor diode. There are 2 parts of the experiment. There's the intrinsic band gap determination, which uses a temperature probe and the diodes hooked up to a circuit while the diode is heated to determine the intrinsic band gap. Logger Pro software was used to plot the relationship between the measured voltage and temperature. So all 5 LEDs and the silicon diode were analyzed using the setup seen on the right. For experiment 2, active band gap was analyzed using the emission spectra created using ocean optic spectrometer and a fiber optics cable. The fiber optic cable was pointed at each LED to obtain an emission spectra, and the wavelength of maximum intensity was noted for later analysis. The silicon diode was chosen to act as a verification method. It's an insulator at room temperature, meaning the population ratio is at 0 at room temperature. It's made into a semiconductor by adding heat or dopant chemicals that allow for the transfer of electrons. When heat is added, electrons drop from the conduction band into the valence band, enabling the measurement of the intrinsic band gap. A graph was created with the 1 over temperature on the x-axis and the voltage over temperature on the y-axis to create a linear regression that would match the form of equation 1. The resulting equation would have the intrinsic band gap energy as the slope of the line. The experimental energy of 0.9729 electron volts was compared to the literature value of 1.12 electron volts to obtain a percent error of 13.13%. It is important to note here that using heat as a means to create an intrinsic semiconductor is not an efficient or feasible means in a long-term setting, as the heat needed to generate this conduction is too high for everyday use. This same process was recreated for each of the 5 LEDs. So for the first 3 LEDs made of aluminum and gallium, the same analysis was created and run to determine the intrinsic band gap energy. The intrinsic band gap energy increased as the emitted wavelength decreased, as red had the smallest intrinsic band gap and yellow had the largest. For the indium gallium LEDs, green was found to have a larger band gap energy than blue. Next, the active band gap energy was determined using the highest wavelength on the curve, as shown by the green arrow on this blue curve right here, around 530. This was completed after the emission spectra was normalized in an Excel to allow for easier calculations. The active band gap was determined first in joules using equation 2, as seen up here, and then it was converted into electron volts. The active band gap energy increased with decreasing wavelengths, as blue had the largest energy and red had the smallest. Next, the band gap width was determined using full width half max, as shown in the figure on the right. The width is the distance between where most of the transitions are occurring in the 2 bands. Since the spectrum was normalized, the half max occurred right around 0.5 intensity. The wavelengths for each of these were marked, as shown on the graph, and then the upper and the lower bounds were subtracted to find the distance in nanometers. Blue had the largest width and yellow had the smallest. The final analysis was completed to determine the dopant ratio for both types of diodes. For the aluminum gallium diodes, the relationship shown in equation 3 up here was plotted for 20 points between 0 and 1 and resulted in a linear graph. Then, this equation was solved for X, which is the aluminum ratio, for each of the 3 diodes, red, orange, and yellow. Red had the smallest ratio of aluminum to gallium, and yellow had the highest. This was once again completed for the indium gallium diodes. Equation 4 up here was plotted for 20 values between 0 and 1, with X being the ratio of indium and Eg being the band gap energy. This was then solved for X, and since it is a quadratic, the value lower than 1 is used to be the ratio of indium. The green had the highest amount of indium compared to blue. For this experiment, trends can be observed for both types of diodes. For the aluminum gallium diodes, the active and intrinsic energies are positively related and inversely related to the band gap width. The band gap width shows that the highest prevalence of transition occurs at a closer distance in yellow diodes compared to the red diodes with the highest energy. The increase in energy results in a shorter wavelength, which is shown by the yellow light emitted. Additionally, this increase in aluminum dopant content results in a higher band gap energy. This is due to the small atomic size of the aluminum dopant increasing the covalent bond overlap and then increasing the conduction, which results in a higher energy. For the blue and green indium and gallium diodes, the results were slightly different. The intrinsic and active band gap energies were inversely proportional, whereas the previous diodes had a directly proportional relationship. Furthermore, the active band gap energy was directly proportional to the band gap width. This change in trends is due to the increased orbital size of indium. The intrinsic band gap is inversely proportional to the ratio of indium, as the indium decreases the bonding overlap and therefore decreases the energy. The active band gap still trends with the emitted wavelength as expected, with a higher energy resulting in a shorter visible wavelength.